Welcome. Okay, today we're going to do some problems in Laplace transforms from Schwamm's outline series. And so have a look at the top. The definition of the Laplace transform is the Laplace transform of the function of x is the integral from 0 to infinite e to the minus sx times f of x with respect to x. The purpose of the Laplace transform is to be able to solve initial value problems, and especially so when there involves a piecewise function. So some engineering and physics problems involve switches, and hence a piecewise function in the differential equation. Laplace transforms are really good at that. All right, so let's do this with our first problem, question 1. So we're taking the Laplace transform of x squared, and we're supposed to get 2 over s cubed. So we need to set this function x squared in our integral, and then integrate this. Now I think it's pretty clear here that we're going to need integration by parts to finish this off. So let's trade this e to the minus sx in for a derivative so that we can use integration by parts. Okay, so then we have integral from 0 to infinite x squared d e to the minus sx with respect to x dx. But that's not quite true there. Let's make that true. Now, if we were to actually differentiate this, using the chain rule, we would bring down an extra minus s, which we want to cancel. So we need to insert here minus 1 on s to make this true. Okay, so now that we have a true statement, let's keep going. So with this, I can pull this out of the front because I treat that s as a constant here. So minus 1 on s, integral from 0 to infinite, x squared with respect to e to the minus sx by substitution. Okay, next, let's use that integration by parts formula. So here then we have the product of these two. So x squared e to the minus sx, 0 to infinite, and then we subtract. This comes along, but I'm subtracting. Okay, and then we swap these, put them the other way around. So the integral of e to the minus sx with respect to x squared. And now remember what you can do. You can put in dx dx. So we can view this part as a derivative by a substitution. Now the derivative of x squared with respect to x is 2x. So let's simplify this here. Okay, so we should come along and not insert that infinite there, but take a limit. So minus 1 on s, and so inside the brackets we have the limit as x goes to infinite of x squared over e to the sx, and then we subtract what happens when we sub in that 0 in for x. So we have 0 squared over e to the power of 0. And then continuing on with this, we have plus for the 2 minus signs, so plus 1 on s. Integral of, now the derivative of x squared is 2x, so we can even pull the 2 out and call this 2 on s. And so we have x e to the minus sx dx. Now, you see this has gone down from here. It's gone down 1 degree. And so it's not done, but we're getting closer. Okay, so let's continue this. Now, in this line, what we have then is 0 for this limit because e to the sx grows faster than x squared, provided that s is positive. Okay, and so we'll get a limit of 0 for that. Now over here, we have 0. Okay, and so that's 0 plus 2 over s, integral 0 to infinite. Now again, let's trade this e to the minus sx in for a derivative. But to do that properly, we need to divide by the minus s. So out here, let's put that 1 on minus s. Okay, and then I've neglected to put the over dx because we're just going to get rid of those anyway. Okay, so next, let's simplify this. So we have minus 2 over s squared. And then using the product rule, we'll have x e to the minus sx. I said product rule, but it's integration by parts, which is related to the product rule, isn't it? Okay, and then we are subtracting minus 2 over s squared, integral from 0 to infinite, e to the minus sx with respect to x. So just taking those and swap them. Okay, so let's continue on. So this one, again, we're going to get 0 for this part because we take a limit for this piece as x goes to infinite. We get 0. And then we also get 0 when we sub in the 0 there. So then we have 0 plus 2 over s squared. Integral of e to the minus s is 1 on minus s, e to the minus sx, 0 to infinite, and we're almost done with this. 2 over s squared, limit as x goes to infinite. Well, let's also bring that minus 1 over s out the front. Okay, e to the minus sx. And then we subtract e to the 0. Okay, now this limit here is 0, and this is 1. So we have minus 1 on s, 2 on s squared, brackets times minus 1, and this gives us 2 over s cubed. Okay, and we got exactly what we're hoping to get there in that question.
Yeah, it's that simple.
Question 2, show that the Laplace transform of e to the ax is 1 over s minus a for s greater than a. So we need to use our definition. Laplace transform of e to the ax is the integral from 0 to infinite e to the minus sx e to the ax dx. Okay, we have the same base e there. We can add our exponents. So e to the a minus s in brackets x dx. We treat the a minus s as a constant in this integral. And so integrating this, we have e to the a minus s brackets times x. But if we were to differentiate this, we would bring down an a minus s. So we need to divide by that here. Okay, this is a definite integral, so we put in our square brackets saying that we are going to take a limit and sub in 0. Okay, so let's do exactly that. And we'll pull out the 1 over a minus s out the front. And so we then have limit as x goes to infinite, e to the a minus s brackets times x. And then we're subtracting e to the 0, because if we sub in 0 there for that x, we have a minus s brackets times 0 is 0. Okay, now this limit here depends on the sign of that exponent a minus s. So if a minus s is positive, then that diverges. It's not a number, it's not finite. But if a minus s is negative, then that's different. That limit then in that case is 0. And then minus 1. And let's put the clause if a minus s is negative. Okay, so simplifying this, we have minus 1 over a minus s, provided that, let's rearrange this so that we add s to both sides. So if a is less than s. Okay, now we can multiply top and bottom of this fraction by minus 1 and say that this is 1 over s minus a if, let's just swap the order of these, but it says the same thing, if s is greater than a. But more precisely, because we assume that s is a complex number, so let's say more precisely, if the real part of s is greater than a.
See, not so scary.
Okay, question 3. Take the Laplace transform of this piecewise function. So to do that, we need to set up our definition. Laplace transform of f of x is the integral from 0 to infinite of f of x e to the minus sx with respect to x, but this is a piecewise function, so what we want to do then is break this integral up at the place where this changes, and so then we have the integral from 0 to 2, and then we add to that the integral from 2 to infinite. Now if x is greater than 2, we have 3. Okay, so over here I see that I should have put e to the power of x, because if x is less than or equal to 2, we have e to the power of x. All right, then e to the minus sx with respect to x. Okay, so let's finish off this integral then. So we have e to the power of 1 minus s outside of x. And then over here, let's just rewrite that. Okay, so now let's integrate these. They're both easy to integrate. So we have 1 over 1 minus s, e to the 1 minus s times x between 0 and 2. And then over here, 3 over minus s, e to the minus sx, 2 infinite. Okay, so finishing this one then, we have 1 over 1 minus s brackets e to the 2 1 minus s minus e to the 0. And then for this, minus 3 over s. Now the limit as x goes to infinite of e to the minus sx is 0. I'll put in brackets 0, and then minus e to the minus 2s. Okay, so we need to simplify this. So 1 over 1 minus s, e to the 2 minus 2s, then subtract 1. And then over here we have plus 3 over s, e to the minus 2s. Okay, now question 4. We are asked to take the Laplace transform of 2x squared minus 3x plus 4, but this doesn't say using the definition. So let's just use what we already have, that this is twice the Laplace transform of x squared minus 3 times the Laplace transform of x plus the Laplace transform of this constant 4. And when I say let's use what we already have, we know the Laplace transform of x squared because we have already done that the hard way. So that's 2 times Laplace transform of x squared is 2 over s cubed. And then the Laplace transform of x is 1 over s squared. And then the Laplace transform of the constant 4 is that constant 4 over s. Okay, and so I have a little cheat sheet here with these things on it. Except this is expressed in terms of t here. Okay, Laplace transform of a constant is the constant over s. And then up here, the Laplace transform of t to the n is n factorial s to the n plus 1. So the Laplace transform of x to the n is n factorial over s to the n plus 1 also. So let's simplify this here. So we have 4 over s cubed minus 3 over s squared plus 4 over s. And we can even factorize this if we want to, multiplying top and bottom of this one by s and top and bottom of this one by s squared. So we have 4 minus 3s plus 4s squared all over s cubed. Okay, and I want to take this opportunity to open up Mathematica with you and show you how we can verify the Laplace transform of a function. Okay, so let's run that. So this is what it gives us, exactly what we have on this line. But let's also factorize that so that we can show the line that we have below that as well. All right, great. And so this works on much harder examples also. Okay, question 5. Take the Laplace transform of x e to the 4x using the definition. And so that's the integral from 0 to infinite of e to the minus sx x e to the 4x with respect to x. So we have the integral from 0 to infinite of x e to the power of 4 minus s, all in brackets times x, integrated with respect to x. All right, so with this one, we will need to use the integration by parts formula. So we will integrate e to the 4 minus s all times x first to express it as a derivative. Now, when we do that, we need to compensate here by putting in 4 minus s on our denominator of a fraction, so that when we actually differentiate this, the 4 minus s that would come down using the chain rule would cancel with this one to make this true. Okay, and so simplifying that, we can bring this out the front. So 1 over 4 minus s, integral from 0 to infinite of x with respect to e to the 4 minus s brackets x. Okay, so now that we have this in this very simple looking form, we can use the integration by parts formula. So let's come over here because it's going to take a little bit of space. 1 over 4 minus s brackets the product of the two of those, x e to the 4 minus s x, 0 to infinite. And then we subtract and we just swap the roles of those. But the 1 over 4 minus s has to come with us here. Okay, and so let's simplify this. Now, this part of it here requires a limit for the infinite. So let's write s minus 4 brackets x there. So I've taken that down to the denominator, and when I do that, I need to change the sign of the exponent, but that swaps around the order of this difference. Okay, and now I'm doing this under the condition here that s minus 4 is positive. So if s is greater than 4, in other words, and then we have minus 0 for when we sub in 0 there. Okay, let's end that bracket, and then we'll just do this integral here also. So we have minus 1 over 4 minus s. And when we integrate this, we have another 1 on 4 minus s, e to the 4 minus s, x, 0, infinite. Okay. Moving on. Now, provided that s is greater than 4, s minus 4 is positive, so this limit will give us 0 in here. Okay, so this is all 0, all of this. And then over here, let's keep going. So we have minus 1 over 4 minus s squared, limit as x goes to infinite, e to the minus in brackets s minus 4x. Okay, because we have assumed here s is greater than 4. And then we subtract e to the 0. All right, so continuing, this limit here is 0. This is 1, so we have minus 1 inside the bracket. And so we get 1 over 4 minus s all squared, because the product of minus 1 and minus 1 is plus 1. And let's just remind ourselves that's if s is greater than 4. Okay, so because that was a tricky one, let's go to Mathematica and get Mathematica to calculate the Laplace transform of x e to the 4x also. X exp 4x. All right, and it has given us the same thing, 1 over minus 4 plus s all squared, but that is the same as this because we have a square there. Okay, question 6. Laplace transform of e to the 2x is integral 0 to infinite e to the minus sx e to the 2x dx. So this is your integral from 0 to infinite e to the 2 minus s in brackets x dx. So we have 1 on 2 minus s e to the 2 minus s x brackets 0 infinite. Okay, and so we take a limit for the first one, and we get 0 for that limit, provided that 2 minus s is negative. So 0 minus 1 on 2 minus s e to the 0, and that's if 2 minus s is less than 0. All right, and so this is 1 over s minus 2 if s is greater than 2. Now, that agrees with what we have in question 2. All right, question 7. Calculate the Laplace transform of x using the definition. So the integral from 0 to infinite of x e to the minus sx dx. Okay, we turn that e to the minus sx into a derivative, but doing that involves dividing by minus s. And then getting rid of the dx, so that this is the integral of x with respect to e to the minus sx. Now let's use integration by parts on this. Take the product of the x and the e to the minus sx. And then we swap around. Swapping the roles of these two. Okay, and now let's finish this off. So the limit as x approaches infinite for this is going to be 0. And then when we sub in 0, we also have 0. So 0, 2 minuses multiply together to give a positive. So 1 on s. Now the integral of e to the minus sx with respect to x is 1 on minus s e to the minus sx 0 infinite. Okay, nearly done with this one. So we have minus 1 on s squared, then limit as x approaches infinite, e to the minus sx minus e to the 0. Now, if s is positive, then this limit exists and is equal to 0. Okay, and so e to the 0 is 1, so we have minus 1 on s squared times minus 1 if s is positive. And so we get 1 on s squared. Question 8. So in question 8, we have Laplace transform of x e to the minus 8x. So integral 0 to infinite x e to the minus 8x e to the minus sx integrated with respect to x. So we have minus s minus 8 brackets x. Okay, so we need to swap this for a derivative. And so when we do that, we divide by minus s minus 8. Okay, now we can use integration by parts. And so we take the product of these two. And then we swap the roles of these in a subtraction. And then we take a limit for this one. And so we'll get 0 for that limit, provided that s plus 8 is positive. If s plus 8 is positive. Okay, so let's finish this one now. So we have minus 1 on s plus 8 squared. And then for this, that limit will give us 0. And then we subtract e to the 0, which is 1. And so we're going to get s plus 8 to the power of minus 2. Or you could write this as 1 over s plus 8 squared. Okay. Okay, inverse Laplace transforms. So let's have a look at question 9, where we are asked to take the inverse Laplace transform of 1 over s minus 8. Now, we already know, based on the problems that we've done, that the Laplace transform of e to the ax is 1 over s minus a for s greater than a. And so if we're attempting to go backwards, applying the inverse Laplace transforms to both sides of the equation expressed in question 2, we would get e to the power of 8x. And so this is just e to the power of 8x. Okay, question 10. Calculate the Laplace transform, or the inverse Laplace transform of 1 over the square root of s. Okay, now for this one, we want to write this as inverse Laplace transform of 1 on the square root of pi times the square root of pi over the square root of s. And then this 1 on root pi can come through that operator, Laplace inverse. So we have 1 on the square root of pi, inverse Laplace transform of the square root of pi over the square root of s. Okay, and then in a lookup table, you can look this up, that we're going to get for this Laplace transform here, we're going 1 on root s for this, and we have 1 on root pi here. Okay, in Mathematica, let's do this. So I'll write inverse Laplace transform. Then I'll put 1 over sqrt s, comma, s, and then the x, and then run that. And so that gives us, and I see I should have written 1 on the square root of x here. Of course, we're going the other way, aren't we? So we get 1 on root pi, 1 on root x. Okay, question 11. Laplace inverse of s over s minus 2 squared plus 9. So we want to write this in the numerator with an s minus 2 in it. So we'll express this as Laplace inverse of s minus 2 plus 2 over s minus 2 squared plus 9. And now we can break this up as a sum of two fractions. So we have Laplace inverse of s minus 2 over s minus 2 squared plus 9. And then plus Laplace inverse of 2 over s minus 2 squared plus 9. Okay, because we know what this Laplace inverse is, and we know what this inverse Laplace transform is. So for the first one, we've got e to the 2x cos of 3x. And then we've got 2/3. So bringing out the 2 and recognizing that 3 squared is 9. 2/3 e to the 2x sine of 3x. Okay, let's verify this in Mathematica. Now it's given us something rather strange looking for the inverse Laplace transform of this, but what we can do is use the fact that e to the theta I is cos theta plus I sine theta. Okay, so we have this, and now we might want to expand and collect like terms or use various trigonometric identities to see that we get this. Okay, so cos of minus 3x is cos of 3x, sine of minus 3x is minus sine of 3x. So if we were to expand this, well, we get a bit of a mess, don't we? How about I just verify this another way without using identities? If I just say Laplace transform of cos of 3x exp 2x. Okay, so we can see that we get exactly that there. Okay, so now let's do the same thing for 2/3 sine of 3x e to the 2x. Okay, so we get 2 over s minus 2 squared and then plus 9. Okay, question 12, Laplace inverse of minus 2 over s minus 2. We can write this as minus 2 Laplace inverse of 1 over s minus 2. And so this is minus 2 e to the 2x. Okay, question 13. Inverse Laplace of s over s plus 1 squared plus 5. So we want to write this as inverse Laplace of s plus 1 over s plus 1 squared plus the square root of 5 squared. And then minus 1 on the square root of 5, Laplace inverse of root 5. Because remember, 1 on root 5 times root 5 is 1. So that's why I put the minus there. So it cancels this 1 in there. So we in fact have the s. Okay, so this is root 5 over s plus 1 squared plus root 5 squared in that big bracket. Okay, Great. So now that we have this, we can look these up in our table and see that this is e to the x cos of root 5 x, and then minus 1 on root 5 for this one, sine of root 5 x. Okay, question 14. Inverse Laplace transform of 2 over s squared s minus 1 s squared plus 1. Now what we want to do with this is break this fraction up using partial fractions and writing this as a over s minus 1 plus bs plus c over s squared plus 1. Now we've got to find the a, b, and the c, so we need to put this back together and make it look like this. So to do that, we have a s squared plus a for this times this, and then this times this will give us plus b s squared plus cs minus bs minus c, and that's all over the product. But we want this numerator to be 2s squared. So we need to seek a, b, and c such that we get 2s squared out of this. Okay, so let's collect in terms of s. So we have a plus b outside of s squared, and then here we have plus c minus b times s, and then we have plus a minus c is 2s squared. Okay, so that gives us 3 equations. A plus b is 2. C minus b is 0 because there are no single s's over on the right-hand side. And a minus c is 0 as well. Okay, so this second equation tells us that c is equal to b. And over here, a is equal to c is equal to b from there. Okay, then, so the top line gives us 2a because b is equal to a. 2a is equal to 2, so a is equal to 1, b is equal to 1, and c is equal to 1. All right, and so then we're supposed to have 2s squared over s minus 1, s squared plus 1 equal to 1 over s minus 1 plus s plus 1 over s squared plus 1. Okay, now for this one, we want to break this one up further. So s over s squared plus 1, and then plus 1 over s squared plus 1. So now if we take the inverse Laplace transform of this, it's easily possible. Okay, so for this, we should get e to the x. For this here, we should get cos of x. And for this, we should get sine of x. Okay, the purpose of the Laplace transform is to be able to solve initial value problems, and especially so when there involves a piecewise function. So some engineering and physics problems involve switches, and hence a piecewise function in the differential equation. Laplace transforms are really good at that. Okay, question number 15. Asks us to solve the initial value problem y dash minus 5y equals 0. Y of 0 is 2 using the Laplace transform. Okay, so we have these two which tell us how to take the Laplace transform of y dash and y double dash. So applying the Laplace transform throughout to this equation, we have Laplace y dash minus 5 Laplace transform of y equals the Laplace transform of 0. Okay, now according to this, Laplace transform of y dash is s uppercase y of s minus y of 0. And then we have minus 5. Laplace transform of y is defined as uppercase y of s. I'm going to try my best to make this 5 look like a 5 instead of an s. Be careful yourself. So 5 uppercase y of s. Okay, this is equal to the Laplace transform of 0, which is 0. Remember, the Laplace transform of a constant is the constant over s. Okay, now y of 0 is 2. So we have s minus 5 times y of s equals, when we take this over to the right-hand side, we have equals y of s, which is 2. Okay, and so now we solve for y of s. We have 2 over s minus 5. So now we want to take the inverse Laplace transform of both sides of this equation, and magically we're going to get the solution. Okay, so taking the inverse Laplace transform of both sides, now the inverse Laplace transform of uppercase y of s is lowercase y as a function of the independent variable. In this case, let's call it x. So y of x is this. All right, now we need to take the inverse Laplace transform of 2 over s minus 5. So this is 2 inverse Laplace of 1 over s minus 5. And the inverse Laplace transform of 1 over s minus 5 is e to the 5x, if we're doing this in terms of x rather than t. So 2e to the power of 5x. Question 16. Y dash plus y equals sine of x. Y of 0 is 1. Okay, taking the Laplace transform of both sides, we have s uppercase y of s minus y of 0, so that's minus 1, then plus uppercase y of s equals the Laplace transform of sine of x. Okay, so I think we had this in a table, but we may as well just use Mathematica to remind ourselves what that was. Okay, and so we have 1 over s squared plus 1. Now, we need to solve for uppercase y of s. So, factorizing that out of these two terms, we have s plus 1, uppercase y of s, equals, taking that minus 1 over to the right-hand side, 1 plus 1 over s squared plus 1. Okay, and so now we need to divide throughout by s plus 1 to get uppercase y of s. So y of s is 1 over s plus 1 plus 1 over s plus 1 s squared plus 1. Okay, and now we would break this up using partial fractions, but what we're going to get when we take the inverse Laplace transform of this is y of x is equal to e to the minus x for this and then plus 1/2 e to the minus x minus 1/2 cos of x plus 1/2 sine of x. Okay, question 17. dn on dt is equal to 0.05, where n of 0 is 20,000. Using the Laplace transform. Okay, so let's take the Laplace transform of both sides of this. So the Laplace transform of n dash is equal to the Laplace transform of 0.05. Now I want to call the Laplace transform of n dash, I want to write that in terms of uppercase y of s so we don't get confused. So then we'll have s uppercase y of s minus n of 0 equals 0.05 over s. No, have I written down the question wrong? Yeah, I have. Yes. I mean, the original question here should be, there's a typo in my PDF there. So let's just insert here an uppercase n. Okay, and so then I'll have to put an uppercase n here, and that makes this not 0.05 over s, but instead 0.05 times the Laplace transform of n, which will be 0.05 y of s. Okay, and so let's bring this over to the left-hand side. So we have s minus 0.05 times y of s is equal to n of 0, which is 20,000. Okay, great. So continuing, dividing throughout by s minus 0.05, we have y of s is equal to 20,000 over s minus 0.05. And now we need to take the inverse Laplace transform of this. So we have y. No, we have n, isn't it? So n as a function of t is the inverse Laplace transform of uppercase y of s, which is inverse Laplace transform of this, but let's write that 20,000 times inverse Laplace transform of 1 over s minus 0.05. Okay, and so on the right-hand side, we have 20,000 e to the power of 0.05 t is n of t. All right, question 18. Y dash plus 5y equals 0. Y of 1 is 0. Do this with the Laplace transform. Okay, let's take the Laplace transform of both sides here. Laplace transform of y dash gives us s uppercase y of s minus y of 0. So let's say let y of 0 be equal to y subscript 0. So here I'll just put y subscript 0. And then we have plus 5 uppercase y of s equals 0. All right, now let's take that y subscript 0 over to the right-hand side. So we have s plus 5 in brackets y of s is equal to y subscript 0. And so then y of s is equal to y0 over s plus 5. Okay, now taking the inverse Laplace transform of this, we have lowercase y of t is equal to y of 0 inverse Laplace of 1 over s plus 5, which is e to the minus 5t. All right, now can we do anything more with that? Okay, so when t is equal to 1, we have y equal to 0. So then that says 0 is equal to y subscript 0 e to the power of minus 5 times 1. So we see then that y0 is e to the power of 5. And hence, y as a function of t is e to the 5 over e to the minus 5t.